Good morning, students. Hi, my name is Lunghile, and I thought I'd get you guys started on COCO. I know it can be quite stressful, especially given these times that you're not having a lot of exposure to your lecturers. You're not on campus. You seem to be alone, and I know this can be quite stressful. So today, what I want to do is I just want to get you started on any simulation environment. To be honest, even if you're using COCO, Aspen, ChemCAD, the general principle is the same. But today we're going to specifically focus on COCO. If you need help with any of the other platforms, whether it be ChemCAD or Aspen, do drop me an email. And then if it's a platform that I've not used before, just send me a link to the platform. If I'll be able to download it, I'll just practice it, and I'll probably be able to help you get started. The important thing is to get started, as your degree depends on it at the end of the day. But the most important thing is not just the degree. It's actually getting an understanding of the simulation environments in order to better improve yourself as a process engineer. So enough of my ranting, let's get started. So first things first, you're going to open the simulation platform on COCO, which is called Coffee. So Coffee is where you're able, it's the interface that you can use to set up your flow sheet. So I'm just going to open that now. So if you have COCO installed, you'll go to Start. Then you'll just look for COCO, and you'll see you have Coffee. Just open Coffee. Now that you're here, this on Coffee, this keeps popping up. In my experience, no matter how many times I try to download the new version, it never does anything. So if anyone knows what to do here, please give me a shout. So first things first, here's your simulation environment. So I'm just gonna put up a simple flow sheet where I'm going to have streams coming in. We're going to heat them up. Then we're going to send them into a reactor, and out of the reactor, we're going to have a simple flash drum just to do a demonstration of separation. And yeah, we're just gonna leave it there. So I'm just gonna choose something simple just to get you started. Okay. So first things first, let's choose the initial equipment. We said we're going to heat up the incoming streams. Okay, so let's take a mixer, for example. Let's go. So that's a mixer, and then you put it there. Now you'd have two incoming streams. Inlet 1, and then we have another incoming stream, inlet 2, and then we put in an outlet stream. Now you'll notice that everything is dark green, and if I click on stream 1, there is nothing there. You can only input your pressures, but there are no components. And I deliberately did this to just show you what happens. You can set up your whole flow sheet, but if you haven't defined the system you're working with, then nothing will happen. So let me take you through that. We're going to choose one of the preset property packages with compounds that COCO has, and we're going to use that as an example. So if you come here to the taskbar, you'll see the two test tubes. If you click on that, it will say configure flowsheet, right? And then what you'll then do is there's that certain options. There is property packages, stream types, flowsheet, reaction package, compounds, appearance. The first one we're going to look at is the property packages. So you're going to go add, And then we can either do ChemSep property package manager or TEA. I usually prefer TEA, but either way, both work quite well. And as you get used to COCO, you'll be able to choose whichever one works best for you. So let's start with the TEA. Let's give it a second. And you'll see here there are a couple of options. Alkanes, let's see what that consists of. If we go in here, we'll go edit. It has alkanes up to C10, right? That could be one option we could use. What are the other options that we have? Let's just go cancel, and then let's remove this one. Remove. We just want to look at the various options. Let's go add again, and again TEA. Let's look at HDA, and then we go select. And HDA, what do you have in store for us? It's got hydrogen, methane, benzene, toluene, and biphenyl. Let's go with that, just for interest's sake. All right. So next, so we've got those compounds. Maybe so we've got hydrogen, methane. We've got hydrogen, methane, benzene, toluene, and biphenyl. Okay, let's close that. Before we do, maybe let's add water for interest's sake, just to see what happens. So we've got that. Then we'll go edit. Now, when you go edit, you can add a compound. So let's add water. Let's add water. Hydrogen we already have. Maybe let's add carbon monoxide. Just want to give it. I'll explain why I'm doing this when we get to the reactor. Okay. All right. Then we close that, and everything has been applied. So now let's just define our streams. So the first one, let's use bars, and let's work with a pressure of 3 bar, right? And then temperature, let's start off at 298.15 Kelvin, right? And then in the incoming stream, let's have, let's see, let's have 0.3 of hydrogen. Let's have not methane. Let's have some benzene, 0.7. And then let's have 0 of the rest. Right? And then let's have a flow rate of 5 kilomoles. Right? And then let's go back to the flow sheet. And here, let's just add water. So again, let's put it in a 3 bar. Let's put it in a 298.15. And then we're going to have 0, 0, 0, 0, 0, and then mole fraction of 1 for water. Excuse me, I should have said that before. We're adding mole fractions. So as you well know, mole fractions is from 0 to 1. And then let's have that. I don't know why we have that as kgs. Let's have that as kilomole per second. Again, let's have that as 3 kilomoles. I think I made that same mistake with the, let's have that as 3 kilomoles as well. Okay, if we run that, you will notice that everything is now green. That is to show you that everything is working well, and you will see that your output stream is now a mixture of everything that of the two streams that we had coming in. Okay, so now let's hit up. Obviously, as I said, we're just playing around just to see what will happen. So let's hit up the stream. I just want to take you through each point just to show you certain features of COCO. So let's take a heater cooler, select, and let's join our stream. The moment we join it, and then let's have an output stream. You'll see that the output stream is still dark green, showing nothing has happened. The exchange is black, showing it you can run, but let's just first change the temperature. And let's take it to, so we're 298, let's take it to 398.15, so increase by 100 degrees. Right? Now let's run again. Now, what I want to show you now is the vapor liquid equilibrium of the states of the streams. So now let's look at the stream coming in at 229 Kelvin. You can come to phase fractions and you'll see that you've got 84% liquid and 15% vapor. Now, let's go to the output stream 4 and look at the phases again. Now you've got complete vapor. We will come back to the phase distribution later when we look at separation, especially based on VLE using using something like a flash drum. So now let's put in a reactor. And when I actually started this today, the first thing I thought of was a Gibbs reactor. And the reason for that is I feel it's the simplest reactor to use, but also it's the most practical when you do not have much information about the reaction itself. So given that you don't have the kinetics, you don't have information on the conversion that you require to have all those things. This is the most simplest one to use because what it does is it takes you to the equilibrium conversion based on the conditions that you have. So the Gibbs reactor, put it down. As I said, we have no idea what will happen. We just took the HDA property package. We put water into the system. We also defined that CO is a possible product. We're not sure. It might not even come out. So let's double click on that. And then if you click edit, you will see that there's reaction specified by compounds, right? And then vapor. Now, in other cases, and we can look at another lesson, we can look at your fixed conversion reactor. It will require you to assign a reaction package. But in this case, with the Gibbs reactor, you don't need to. You can, but you don't need to. And then you'll come here to reactive compounds, and let's select everything. What will happen is, based on the compounds that you have, right? The Gibbs reactor will give you possible reactions that can come out from the system, right? And that again will then be based on what? So the principle that it uses, it's the Gibbs minimization energy, which you can read about in your, I think Perry's has something on that. Most thermodynamics textbooks should have a discussion on that. I haven't looked at it in a while, but the point is it does your reaction based on the Gibbs minimization energy. And we close that. And let's run our reaction at 398.15 Kelvin. Run. It says failed to solve. Solution converts to an invalid solution. Okay. Let's go back. Actions. So we had our reactions. So who's giving us a problem? Specify compounds, it's in vapor phase. See what happens if we increase the temperature. Let's take this to 498.15. Again, it's not running. Let's remove one of our reactive compounds. So let's remove carbon monoxide, as it was not part of the system in the first place. And you'll see that the no compound water is the only compound. Oh, huge. So water could have been the problem in the first place. So let's see if we add back. Okay. Let's move that. Let's see. So those were our two problems. Now we run again. And now we've got reaction. So the one thing you saw there is that the Gibbs reactor will look at the compounds that were given, and you've specified as reactive compounds, and give you the reactions that are possible based on those compounds that you put in. Now, should there be a compound that would form an imbalance in the possible reactions, it will not allow you to run. So let's look at our products. So now you can see that we've got hydrogen, methane, we've got benzene, toluene, biphenyl, water, and carbon monoxide. As you remember, our input, we did not have toluene, biphenyl, and we did not have methane, whereas now we have all of those, right? So next, before we go through, I want us to look at our phases. We've still got what? A vapor fraction of 1. Now, I want us to try out the wrong way of trying to separate out the stream into its liquid and vapor components. So let's then take a separator, and we're going to use a flash drum. Select. Put our flash drum there. Let's make it a bit bigger. And we will simply just connect the stream. Have the output stream. Right. And that's on. Now, if we look at this, I should expect nothing on the liquid stream. So it's even reporting vapor, which obviously you expect liquid at the bottom stream, and it's 100% vapor. So your temperature is high. So as you can see, something is not right. So everything has, practically everything has reported to your liquid stream, to your vapor stream. So now, let's actually do what we were supposed to do, and start off by cooling the stream so that we can have a vapor and a liquid separation even before flash drum. Okay. And then we are at 498. Let's take it back to room temperature. So let's take it back to 298.15. And let's have this vessel sitting at the same 298.15. Close that. And let's run again. And now, before we even look at the results, you can see that we now have a 22% vapor fraction and a 77% liquid fraction. And that's quite obvious that the lower the temperature, obviously your condensables will start condensing. I mean, that's the obvious part. And now you see that you've now separated out your heavies, what would be your toluene, your benzene. So this will mainly have water, toluene, benzene, biphenyl, And then if you look at your gaseous stream, you have your hydrogen, your methane, a little bit of benzene, but trace amounts of the rest, okay, and a bit of water in vapor form. So yes, this is how you set up your simple simulation. So now let's go back to the lessons that we picked up. The first one would be at the reactor. As you saw, we had compounds that were not supposed to be there, and the Gibbs reactor just said no. So when using the Gibbs reactor or any kind of reaction system on COCO, you need to understand the reaction itself. So it is important for you to know exactly what reaction you're working with, what you're planning to achieve, and understand not only what the reactants are, but also the products, because you need to tell COCO that this is the reaction, these are the compounds that these are my reagents, and these are the products that I'm expecting, so that it can give you the different combinations, especially when using a Gibbs reactor. When using another reactor, for example, a fixed conversion reactor, where you know your reactor, you know your reactions, you know your conversions, you know your selectivities, in that case, you need to be able to define exactly what's going to happen. So you need to define what are the components, what are the flow rates, what are the products, what is the composition of the product stream, what are the selectivities, what's the conversion. You need to know all of that. But anyways, so that's the beauty of COCO. As I said, any questions, please feel free to send me an email. I will leave my email address on the link below. Otherwise, lots of luck in your studies in 2021. Just know you're not alone. We are, and when I say we, there are a lot of people who've done design before who will be willing to show you in the right direction. Just take your time to look for us. Sometimes it's important, for people who want to help, to actually see that you want to be helped. We won't come looking for you. That little initiative from you gives us that surety that you want to get on with your course. Thank you very much and have a lovely day.